In this video, we're going to talk about indeterminate form and L'Hopital's rule. First letter state L'Hopital's rule. Basically says that if you have a limit as x goes to some value, or plus or minus infinity, of f of x over g of x, and what you get by direct substitution is either 0 over 0 or infinity over infinity. You can take, so let's write this down, 0 over 0 or infinity over infinity. Then that limit equals, the limit as x goes to c of f prime of x over g prime of x. Now, f prime of x is just the name of a function, and g prime of x is just a name of a function. At this point right here, you already took the derivatives, so you don't even have to think of it as a derivative. Maybe it's big F of x, and this is big G of x. Well, if again you get an indeterminate form, 0 over 0 or infinity over infinity, well then you can take the limit again. By taking a derivative of the top and taking a derivative of the bottom. You can keep doing this as long as you get an indeterminate form, 0 over 0 or infinity over infinity. So here's a problem that you learned last semester in Calculus 1. The limit as x goes to 0 of sine x over x. Well, the sine of 0 is 0, and if x is 0 it's 0. This is indeterminate form. Well, now you can just take the derivative of the top, cosine x, take the derivative of the bottom, which is 1, and now substitute in 0. So you get cosine of 0 over 1, which is 1 over 1, which is 1. Just like last semester, the limit of that function as x goes to 0 is in fact 1. It's not going to change. If you have the limit as x goes to 3 of x squared minus 9 over x minus 3, well, 3 squared is 9, take away 9 is 0, 3 minus 3 is 0, 0 over 0. Now last semester you were told to factor the top. Since top and bottom are polynomials and 3 made, in this case, the top 0, then x minus 3 will be a factor of the top. The other factor is x plus 3. You divide by x minus 3. This fraction is not always 1. Not when x is 3. 3 minus 3 is 0. 0 over 0 is not 0. Sorry, is not 1. Any other time, if x is not 3, this over this is 1. Ooh, look at how lucky we are. X is approaching 3. It will never ever be 3. So this is the limit as x goes to 3 of 1 times x plus 3 or x plus 3. Now when we substitute, we get 6. After getting 0 over 0, what I just boxed, that's the Calc 1 way of handling this. Now, armed with L'Hopital rules. Actually, you do learn now armed with L'Hopital's rule, we take the derivative of the top and we put it in the top. We take the derivative of the bottom, which is 1, we put it in the bottom. Well, this is just 2x. The limit as x goes to 3 of 2x is 2 times 3 or 6. So we got the same answers, but using calculus is easier. What do I mean by calculus? We took the derivative of the top as a nice simple polynomial. We took the derivative of the bottom, we got a constant. And then we said, oh, this is 2x, 2 times 3 is 6. Over here we had to know how to factor. And we had a lot of students who will just cross this out blindly anyways. But you really should know that x minus 3 divided by x minus 3 is not always 1. It is when x is not 3. Ooh, x is never going to be 3. So we can cross it off. Let us look at the next problem. Suppose you have a limit as x goes to infinity of 3x plus 2 all over 2x squared plus 5. If you directly substitute, 3 times infinity plus 2 is infinity, 2 times infinity squared plus 5 is infinity. By the way, I want to go and update something that I wrote. You can have plus or minus infinity over plus or minus infinity. That's 4 cases. You can have positive over positive. You can have positive over negative. You can have negative over positive. Or you can have negative over negative. Either one of these tell you can use L'Hopital's rule. Basically because you can always factor out the sign so you get a positive infinity. Okay. So infinity over infinity, that is indeterminate form. We take the derivative of the top, which is 3. We take the derivative of the bottom, which is 4x. We plug in infinity, we get 0. The top goes to 3. The bottom goes to infinity. If you divide 3 by an extremely large number, you're going to get close to 0. And if you divide it by an even larger number, you'll get closer to 0. And a larger number, closer to 0. You can get as close to 0 as you want to. Suppose we have the limit as x goes to infinity of 3x to the 5th plus 2 over x squared plus 2. Okay, I hope you see that this is going to be infinity over infinity. So I take the derivative of the top, and I get 15x to the 4th divided by 2x. Now, depends what you want to do from here. You can say, well, if you want, you can say it's infinity over infinity, and you can use L'Hopital's rule again. So then you're going to get the limit as x goes to infinity of 60x cubed over 2, which is 30x cubed, and x cubed, let's go into infinity, times it by positive 30, goes to positive infinity. What I would probably have done is I would do the division. 15 over 2 is 15 halves, but x to the 4th over x is x cubed. So notice that we're not even taking the same limit. Okay? But we're getting infinity. We're getting infinity. So I reduce first. Once again, you're going to have to know algebra to reduce. Calculus just said take the derivative of the top, take the derivative of the bottom. They're just derivatives of polynomials. Now let us try the next one. Suppose you were asked to calculate this. The limit is x goes to 5 of x squared minus 25 to the second all over x squared minus 25 to the third. Well, if you plugged in 5 squared is 25 minus 25 is 0. Square 0, you get 0. Same thing, 0 as the base. Cube it, you get 0. Now, if you wanted to do it this way, it's going to work. But sometimes it just doesn't pay to use L'Hopital's rule. So you want to take the derivative of this function to a power. Bring down the power, make the new power 1 less, take the derivative of what's inside. The bottom you have x squared minus 25 to the third. The derivative says bring down the power, make the new power 1 less, take the derivative of that, which is 2x. 2 over 2 cancels out to 1, and I checked to see that x was not near 0, so x over x cancels out. So we're left with the limit as x goes to infinity, 2 times x squared minus 25 all over 3 times x squared minus 25 to the second. Well, again, and x is going to 5, excuse me. Again, if you plug in 5, that's going to be 0. That's going to be 0. And when you square to 0, it is still 0. So you take the derivatives of top and bottom again. It will be 2 times the derivative of that, which is 2x, over the 3 stays. We have x squared minus 5 to the second power. Bring down the 2, make the new power 1 less, take the derivative of what's inside. The 2's cancel, the 2x cancels. We are left, so you only have 1 on the top. You are left with the limit as x goes to 5 of 1 over 3 times x squared minus 25. Well, this is going to be undefined because the bottom is 0. Now, here's the case where doing the algebra is going to be much easier. You have the limit as x goes to 5. You have something to the second power. You have the same thing to the third power. You can cancel 2 out on the top, which will give you 0. You can cancel out 2 on the bottom, and the power will be 0. And x minus 25 to the 0 is 1. And in the bottom, you have x squared minus 25 to the first, which is just x squared minus 25. And you get 1 over 0, which is undefined. It looks like the algebra way was just as long as doing this step. Well, what about all the other steps that we did for the calculus? Okay, simplifying first really paid off. X squared minus 25 to the 3 divided by x squared minus 25 to the 3, and the top is 2. I made an error. That's just 1 over x squared minus 25. Know your algebra? You can eat through this problem. Limit as x goes to infinity of e to the x over x squared. Now, everyone's heard people say, oh, that thing grows exponentially. The reason is because that's pretty quick. They don't say it grows at a quadratic rate or a cubic. They say exponential. It grows exponentially. Exponential growth is the largest growth there is. So the numerator, since x is going to infinity, the numerator is growing way, way bigger than the denominator. Why? Because it's growing exponentially. That's just a property of exponential growth. Nothing is faster than that. So since the numerator is growing much, much faster than the denominator, the answer is going to be infinity. And L'Hopital's rule will tell you that. E to the infinity is infinity, and infinity squared is infinity. Now, here's what's going on. The derivative of the top is never going to change, no matter how many times you take the derivative. But the derivative of the bottom is eventually going to become a constant. Right now, it's not a constant. It's still a function of x. So 2 times x, as x grows, so does 2x. Take the derivative again. E to the x on top, 2 on the bottom. This goes to infinity, this stays at 2. Infinity divided by 2 is 2. Sorry, is infinity. 4 divided by 2 is 2. Okay, so basically, the limit as x goes to infinity of e to the x over any polynomial, x to the 100 plus lower terms. So you keep doing L'Hopital's rule, and eventually you'll get down to the limit as x goes to infinity of e to the x over, I don't know, x squared plus 3x plus 1. This equals the limit as x goes to infinity of e to the x over 2x plus 3. And this is going to equal this is still infinity over infinity. Invoke L'Hopital's rule again. And now you get infinity. The one thing I will say is that coefficient of x squared will not be 1. Because the first derivative is going to be 99x to the... It's going to be 100x to the 99. And then it's going to be 100 times 99x to the 98. And then 100 times 99 times 98 x to the 97. Okay, so that coefficient is wrong, but it doesn't matter because I'll call it k. The derivative of kx squared is still 2kx. Okay, and then the derivative of that bottom would just be 2k. And that goes to infinity as long as k is positive. If k is negative, it'll go to negative infinity. Okay, so here's a problem that comes up on all calc books. What is the limit as x goes to 0 plus of x ln of x? Well, should always directly substitute when you're doing limits. And remember that the ln x graph goes like this. That is, as x gets closer and closer to 0, but always positive, because you can't take log of negative numbers. You can't even take log of 0. it's going to negative infinity. So direct substitution, we get 0 times negative infinity. Again, I don't care about whether infinity is positive or negative. Problem here is this is not L'Hopital's rule. It's not 0 over 0. It's not infinity over infinity. So what you have to remember is that any time you want, so this is the same as ln of x times x. You need, or x times ln of x. You need to remember, you can change multiplication. You can change that multiplication to division as long as you flip over that second factor. Most people do it the other way. If you have ln of x divided by ln 1 over x, you keep the numerator, you change division to multiplication, and you flip over the second term. But remember, and this is where I think a lot of teachers blow it when they teach this. They'll teach you that this equals that. And they'll have you do 100 problems to learn how to do that. So little Johnny knows that 2 divided by 3/4 is 2 times 4/3. We kept the 2, we changed division to multiplication, and we flipped it over. But nobody ever told little Johnny that it goes the other way too. I mean, come on folks, that's what equality means. It works both ways. If 2 divided by 3/4 is equal to 2 times 4/3, then there's a rule that says you can keep the first factor, change multiplication to division, and flip over the second number. It goes both ways. Okay, so we're going to think of x times ln of x as this here. Now, when we substitute in a little bit more than 0, we're going to get negative infinity on top. And 1 over x, well, 1 over x looks like this. And it also has this piece. But if I'm a little bit more than 0, I'm going to infinity. And then you say, yes, I can use L'Hopital's rule now. Okay, so this is equal to the derivative of the top, which is 1 over x, and the bottom, which is 1 over x. That's x to the negative 1. So the derivative will be this, negative 1 over x squared. Negative 1 over x squared. Okay, let me get rid of this. Need the space. And we'll use the rule that changes division to multiplication. So I can keep the top, I'll change division to multiplication, and I'll flip that over, which is just negative x squared. And if we simplify this, we get negative x. So we have the limit as x goes to infinity of negative x, which is negative infinity. Okay. Okay, that I just wanted to double check that. So it's negative infinity. So there you had infinity over infinity, or negative infinity over infinity, and that equal to negative infinity. The numerator grew much quicker than the denominator. That is, ln of x grows much quicker than 1 over x. Okay, now let us look at this problem. Suppose you have the limit as x approaches 0 of 1 over x minus 1 over x squared. Well, if you plug in 0, you get infinity minus infinity. And it's understood, in my opinion, that the first one is plus minus infinity. This is indeterminate. The instant one limit is undefined, it's not a real number, I don't care what the rest says. It's indeterminate. So we need to do something to it. For example, if you had the limit as x goes to infinity of x plus 1 minus x, well, this limit goes to infinity, that goes to infinity, yet the answer is 1. Because if you did that subtraction, you're just taking the limit of 1. And the limit of a constant is always that constant. So here I got infinity minus infinity to be 1. That's because I said plus 1. I can get it to equal any constant you want me to get it to equal. I can easily get it to equal k. You pick the k. I can get it equal to k. If you say, I want infinity minus infinity to equal pi, I just plug pi in there, and the answer will be pi. If you prefer it to be negative 3/2, fine. I'll get it to be negative 3/2. I'll get infinity minus, I can give you an example where infinity minus infinity equals any number of your choice. So we need to look at this example a little bit more closely. And I would suggest getting common denominators. So we multiply the top and bottom of the first fraction by 1. So now we have the limit as x goes to 0 of x minus 1 over x squared. So now when you plug in 0, you get negative 1 over 0, which is undefined. Okay? A moment ago it was indeterminate. Now we found out, yep, there's no answer to this problem. Now, the next couple of problems are a little bit different. But let us look at this one first. Suppose you have the limit as x goes to infinity of 12x minus 3x. Well, this is clearly infinity minus infinity. So that means do something. And what I'm going to do is, I'm going to do the subtraction, which is 9x. 9 times infinity, yep, that's infinity. So here we have infinity equal infinity. I got it to equal any real number I wanted. If I want it to equal negative infinity, I'll just reverse this. And I still have infinity minus infinity, but it's really the limit as x goes to infinity of negative 9x. That's negative 9x. So it goes to negative 9 times infinity, which is negative infinity. Let us try these problems. Suppose you have the limit as x approaches 2 of 8 over x squared minus 4 minus 2 over x minus 2. Well, if you plug in 2, the denominators go to 0. They are plus minus infinity minus plus minus infinity. It is indeterminate. So let's see if we can determine it. Let's get a common denominator. This is the limit as x goes to 2 of, Now, the common denominator is x squared minus 4. Well, that's 8 minus, for the second fraction, we have to multiply top and bottom by x plus 2. So the top is going to become, after distributing the 2x plus 4. Limit as x goes to 2. You have 8 minus 2 is 6, minus the 2x. All over x squared minus 4. Okay, sorry, 2x plus 4. I wrote 2x plus 2. 2x plus 4. And 8 minus 4 is 4. Don't forget to take away the 2x. Now, the 4 minus 2x, I can factor out a 2. I get 2 minus x. And the bottom is really x plus 2, x minus 2. X plus 2 times x minus 2. Well, that reduces to negative 1. So we get the limit as x goes to 2 of negative 4. Negative 4 times negative 1 is negative 4. All over x plus 2. Well, that's negative 4 over 4, which is negative 1. So this time, infinity minus infinity is negative 1. You get different answers all the time. Now, suppose we want the limit as x goes to 0 plus of x raised to the 1 over x. Now this one's much more interesting. If you plug in 0, the base will be 0, and the top 1 over 0 is infinity. Now, there's something called a true 0, and I guess not a true 0. This here is not a true 0. For example, if you had the limit as x goes to 0 plus of 0 to the 1 over x. So that means this is getting bigger and bigger and bigger and bigger. But it doesn't matter. 0 is equal to 0 to 1, which equals 0 to 2, which equals 0 to 3, which equals 0 to the 4th, 0 to the 10 million. It's always 0. It's always 0. But that's not a true x. I mean, yes it is, but it's not a true 0. Okay, so 0 to infinity, if it's a true 0, then it's 0. But that's not a true 0. This is getting closer to 0. So what we need to do is first put back that it's indeterminate, and then we need to come up with a completely new way of doing this. Suppose we let y equal x to the 1 over x. And then we take ln of both sides. So we have that ln of y is 1 over x ln of x. Now we can take the limit as x goes to 0. The limit as x goes to 0 plus of the left side, I have no idea what that equals because I don't even know what y equals. Let's work on the right side. So limit as x goes to 0 plus of ln of x over x. That's ln of x over x. And let's see. Remember, ln of a number close to 0 is a negative infinity. And if x goes to 0, well, then it goes to 0. Now, what happens when you do that division? I mean, if you have a large negative number and you divide it by a small positive number, like 1 over this number, no promises I'm going to put the same number as zeros because it's not worth counting. But the rule says keep the numerator the same, change division to multiplication, and flip over that number. Well, this is negative and it is large. It is large. This is approaching negative infinity. This is approaching negative infinity. Okay. Infinity over 0. That's infinity. So what we have is this. ln of y approaches negative infinity as x approaches 0 plus. Now, for example, let's use better values. If I told you that ln of y approaches 3 as x approaches some number, well, if I double both sides, then 2 ln of y would be approaching 6 as x goes to 0 plus. If I divided both sides by 3, ln of y over 3 would be approaching 1 as x goes to infinity. Well, this tells me that y is approaching e to the negative infinity. I guess I can raise both sides to the e, or e to those powers, make the ln y and the negative infinity the powers, and e to the ln of anything is just the anything. Now remember, this is 1 over e to the infinity. So you have 1 and you're dividing it by larger and larger numbers. So it's going to go to 0. And this is as x approaches 0 plus. Now, let us understand this a little bit more. Remember, y was x to the 1 over x. So that is x to the 1 over x approaches 0. Let me just say it here. Y is x to the 1 over x. So x to the 1 over x approaches 0 as x goes to infinity. Well, let's see what that means. As x goes to 0 plus. As x goes to 0 plus, x to the 1 over x approaches 0. As x goes to 0 plus, that's what this says, x to the 1 over x tends to 0. So, there is our answer. Let us try another one. Very similar one. The limit as x goes to infinity of x to the 1 over x. So now we have infinity to the 0. Now, if this were a true 0, no matter what x is, it's never going to be infinity. It's just going to get closer and closer to it. But it'll never reach it. And if you raise any number, whether it's really large or not, to the 0 power, you get 1. But that's not a true 0. It approaches 0. Okay, so this is indeterminate form. So we play the same game. Let y equal x to the 1 over x. Let y equal x to the 1 over x. Then ln of y will equal to it will equal to ln of x to the 1 over x. But I can bring down the 1 over x. So I have ln of y is equal to ln of x over x. And I want to take the limit as x approaches infinity of both sides. And I'm really concerned about the right-hand side. Ln of x over x. Now, ln of x gets larger and larger and larger and larger. It doesn't do so at a very quick rate, but it's larger and larger. Y equal x, it grows much more quickly. And it too goes to infinity. I can use L'Hopital's rule. So it's the limit as x goes to infinity. The derivative of the top is 1 over x. That is, the derivative of ln of x is 1 over x. And the derivative of x is 1. And the rule for dividing by 1 is not to bother. That is, it's just 1 over x. And the numerator is constant, and the bottom's getting bigger and bigger and bigger. This is going to 0. So what we have, and we have it written nice and clearly, the limit as x goes to infinity of ln of y equals this, which equals that, which equals that, which equals that, equals 0. Okay? Now, as x gets bigger, so ln of y gets closer and closer to 0 as x goes to infinity. Well, notice that ln of 1 is 0. Ln of 1 is 0. Okay, so if ln of y is getting closer and closer to 0, that means y is getting closer to 1 as x gets closer to infinity. What does this mean? Remember that y was x to the 1 over x. So, the limit as x goes to infinity, well, this function, the limit as x goes to infinity of that function, well, that function goes to 1. Okay? This is 1. So basically, let me try this out on your calculator. What it's saying is if you do 3 to the 1, let me write it up here. 3 to the 1/3, 4 to the 1/4, 5 to the 1/5, 6 to the 1/6, 7 to the 1/7, eventually 100 to the 1 over 100, eventually 10,000 raised to the 1 over 10,000, 1 million raised to the 1 over 1 million. This is getting closer and closer to 1. I mean, this is not really near 1, maybe not this, but these numbers are close to 1. And if you say no, they're not, I won't argue with you. There's no point in arguing. I'll just say you are right, because you are right. And I'll say, put in some more zeros. 3, 6, 9, 12, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is about 1. Again, if you're going to say, no, it isn't, what are you talking about? Put in some more zeros, 6 more zeros. 1, 2, 3, 4, 5, 6. It's getting closer and closer to 1. In fact, on an exam, if you're allowed to use a calculator, it is easy to see if you're getting the right answer. Infinity, use 10,000. 10,000 to the 1 over 10,000. It should be about what you got your answer to be. If you got 17, well, go back and find your error, because it's not supposed to be 17. In the last problem, in this problem here, we found out that the answer was 0. Okay, so if you take 0.00001, that's x, and raise it to the 1 over 0.00001, you will see that you get about 0. You'll get really close to 0. Okay, that completes this section on indeterminate forms and L'Hopital's rule.